I think we should start. Okay, so I sort of feel like I'm talking loud. I'm gonna turn down the volume just a little. We're kind of in steady state at this point. There's like, I don't know, things are scarily quiet this week. All your responsibility at this point is to be working on MP7, and we're winding things down. So I want to get started on the material for the day because I already know from experience this morning that I'm only going to get through about half the slides anyway. So, and that probably won't even happen if I don't crank through them. So last time we were talking about traversals. Yeah. Last time we were talking about traversals and about how we have a responsibility. A traversal is basically a promise that we're going to visit every vertex and every edge, respecting the connectivity of the graph. Now, you already have experience with the particular traversal that we're going to do today, breadth first search, except that since you already kind of get how it's going to go, I'm going to give you some bookkeeping mechanisms together with the algorithm itself in the context of the example, and then later we'll talk about how we can use, after we execute the whole algorithm, we'll talk about really how we can use all this new additional bookkeeping that we have done. Okay, so what we're going to do is breadth first search on this graph. Now, I'm going to choose an arbitrary starting location. That's something that you're always going to have to do when you're talking about graph traversal, because there's no obvious place to start. Except that that's not true, because I look at that graph and I go, oh, look, the A is at the top. How about if we start with A? Okay, so that's the arbitrariness of it right there. I'm arbitrarily choosing that we are going to start with vertex A. Now, the algorithm itself requires some setup. We're going to do the following. We are going to associate with each vertex in our traversal something we're going to refer to as a predecessor. It's basically, in general, how we got to the current vertex. And in addition, we're going to associate with it a current distance. Okay? So, to initialize the traversal for the first vertex, I'm going to do the following. I'm going to say, well, the distance to vertex A from the start of the algorithm is 0, because that's where we're starting. And the predecessor of A is itself. I'm going to mark vertex A as visited and put it on the queue. All of that is the setup to the algorithm. So let me make just a little note in the margin here of all the things I did for the setup. I initialized D, I set P, I marked the thing as visited. I'll let you decide whether you want this to be a V for visited or a check mark, because it's a Boolean flag that we set. And we put A on the queue. I'll let you decide whether that is the letter Q or an indicator of the Q data structure. Okay, those are just my notes to remind me. Oh, and there's one more thing we're going to add to that in just a minute. In fact, I'm going to leave space for it. Okay, and so now effectively the algorithm begins. Here's the iterative step. Here's what we're going to do every step until the queue is empty. We're going to day Q. I'm going to make note of the fact that A is our current vertex, the current vertex that we're operating from. And note that associated with A, we have all of this data. It's been visited, its predecessor is itself, and its distance is 0. Okay? Now, every iterative step, we're going to do this. We're going to set up a for loop over the incident edges. Okay? I'm going to set up a for loop over the incident edges, and at every iteration of that for loop, that is one edge at a time, I'm going to ask a couple questions. And so I'm standing at vertex A, right here. I have a for loop sitting here. My current iteration of the for loop is focused on vertex C. I'm going to ask 2 questions. Hey, C, have I been to you before? To which C answers, no, C is new. So the vertex on the other side is new, so I don't have to ask another question. Talk about that later. So I'm going to do the following. I'm going to mark the current distance to the new vertex as 1 plus A's. I'm going to make A the, C, we're working on C here. I'm going to make A the predecessor of C. I'm going to mark C as visited. I'm going to mark the edge between A and C as a discovery edge. So that's the part we didn't talk about before because we had no edges. Edge. And finally, I'm going to add C to the queue. Okay, so this is edge. Okay, any question about that? That was a lot. That was a lot of bookkeeping just to process that new vertex. Just to process that new vertex. Okay, but now we're done with it. We're kind of done with C, and we're still processing A's for loop, so we're going to go on to B. The first question we ask is, hey B, have we seen you before? To which B responds, no, B is new, and so we do the following. We update the distance to B. We update the distance to B to be 1 plus A's distance. A's are still our current vertex. Its predecessor is A. It is visited. We mark the edge between A and B as a discovery edge, and we put B on the queue. Okay? Any question about it? Now we're done with B. And now finally, we do the same thing with D. Let's see. The distance to D is 1 plus the distance, or 1 plus A's distance. A is D's predecessor. D is now visited, and we put it on the queue. And now, and we mark the edge, sorry. And now for the first time, we've actually finished a for loop, right? We've finished A's for loop, the for loop associated with A across its incident edges. So we're basically done with A. And so we day Q to get our next thing. And we begin again. So C is live. We're now focused on this row. We're going to set up this whole huge for loop here. And the first iteration in that for loop is to look at vertex B. Hey B, have we been there before? To which the answer is yes. After that, we go, oh, we've been to B before. I wonder if we've been to the edge. Have we been to the edge before? No, the edge is new. And so we designate that edge as something different. This is a new situation. We designate that edge as something called a cross edge. And we'll talk about the reason for that particular word later. Okay, so that's a cross edge. That's a old vertex, new edge, gets the phrase cross edge. Okay. And then we're done. That's all we do. How about CA? Hey A, have we been there before? Yes. Have we seen the edge between them before? Yes. We completely ignore this iteration of the for loop. There is no work to be done here. Keep going. The next one is CD. Have we been to D before? But we haven't seen the edge, so it is a cross edge. That's right. So this edge is a cross edge. Good. And we move on to E. Have we seen E before? No. Oh boy. Okay. E is new. So we're going to do all of these things. We're going to update its distance as 1 plus C's distance, which is, so I'm going to put in a 2 here. E's predecessor is C. We mark it as visited and we put it on the, and we mark the edge between them as discovered and we put E on the Q. Boy, that's a lot. Okay, ready? So we're done with E, and now we move to F. You know the drill. F is new, so we're going to update its distance. It's a 2. Its predecessor is C. We mark it as visited. This is a discovery edge, and we put F on the Q. Any question about it? I'm going to keep going because we don't actually have that much work left here. I know you're bored out of your minds, but we don't have much work left. So let's go ahead and do it. We're going to remove B from the Q. So B is the current active vertex. And we set up the for loop over B's incident edges. What should I do with A? BA. Ignore it because it's done, right? We've been to the vertex, we've seen the edge, we're done there. How about BC? Same, right? We've been to the vertex, we've seen the edge, it's a cross edge, so we're done. How about BE? What do I have to do to process E? Yeah, mark its edge as a cross edge. That's it, and we're done. So see, that was fast. Now we remove D from the Q. Set up the for loop over D's incident edges. What do I do with DA? Ignore. Ignore is going to be a key word for you guys at this point. How about DC? What do I do with DC? Ignore it. Good. How about DF? DF is a cross edge. How about DH? Ugh. It's discovery. It's a discovery edge. Its distance is D's distance plus 1. What am I going to write? 2. Good. Its predecessor is D. It's visited. The edge is discovery. And H goes on the Q. And we're done with D's for loop. So E comes off the Q. What about edge EB? Ignore it. How about edge EC? Ignore it. How about edge EG? Oh my gosh. Okay, we got to do that whole thing again, right? It is EG gets what distance? 3. The predecessor is E. We mark the edge as discovery. We mark the vertex as visited, and we add it to the Q. And we're done with E. We pull from the Q, and we get F. What happens here? FC. Ignore it. FD. Ignore it. FG. Cross. Good. And we're done with F. So then we pull H. HD. Ignore HG is cross. And then we pull G and everything's ignore. Okay? All right. Oh boy, do I have a gazillion. Oh. I have a gazillion questions for you. Okay. Tell me something special about the discovery edges. Oh boy. Tell me something special about the discovery edges. The set of discovery edges all together, yeah? It's a tree, really good. Moreover, it's a tree that hits all of the vertices. So we can call it a spanning tree, okay? Because it hits all the vertices in the graph. All right, and that will always be true for under a little bit of a constraint, okay? It will certainly always be acyclic, let's say it that way. Yeah? Oh, the underline of A, C, and D? No, that was an accident. Here, I can fix it by underlining all of them. There, yes, they're significant. They're all equally significant. Okay, let's see. I have another question. So that was good. So the discovery edges form a spanning tree of the graph. That's kind of cool. What are the D's? What do the D's give you? The values in the D structure? What did you say? Yeah. The minimum distance from each node to A, the start vertex. In breadth first traversal, you will always get that. That's gold. That's valuable. So the way to think about breadth first traversal is sort of as a, I mean, it's level order, right? It's a front and advancing frontier through the graph where you process everything at one distance before you move on to the next level away, to the nodes another step farther, another unit farther from the start. That's true especially of breadth first search, and it will not be true of depth first search. So this is a special moment, okay? Let's see, I have another question for you. Tell me about a graph with no cross edges. What's special about a graph with no cross edges? We've already sort of said this a little bit, but I want to look at it from another perspective. What's true about a graph with no cross edges? Yeah? It's a tree, right? Which means it has no cycles. Now think about this for a second. That means if there's a cross edge, then there is a cycle. So that to me sounds almost like an algorithm for detecting a cycle in a graph. All right, let me see if there's anything else I want to say about this. Oh, let me talk for just a second about these structures, these D and P. You can do a lecture on breadth first traversal without talking about these auxiliary structures, but for lots of graph algorithms, it's very typical to include those structures to aid in decision making for an algorithm. So for example, in the shortest path algorithm, you use P to indicate the current best known direction to pursue in your algorithm, and that gets updated through the course of the algorithm. D is similar. You use D to keep track of the cost associated with, some step of an algorithm. I'm introducing them to you here because in a way they do give you things that help. So we've already said that D gives the shortest distance between A and any other vertex in the graph. So from the start vertex to any other vertex in the graph. But my question is, what is the path that gives you that shortest distance? Where does it live? Where does the actual path live? Yeah? Yeah, exactly. The P's give you that path. So the D's tell you how far it is, and the P's give you the path itself. And what that was, look, this one is the predecessor of G. So G takes you back to E, which takes you back to C, which takes you back to A. Okay? Any question about that? So we're essentially recording our solution, our shortest path solution here. Any questions about it? Okay, so I give you those structures here just because I know that they will be useful to you in the future, not because you need them necessarily for a breadth first search. Okay, so I'm going to show you the pseudocode here, and I want you to ignore this box for now and look only at this box. What I want you to do, so I made a huge mistake here. I forgot to include the D and the P when I wrote this pseudocode. So what I want you to do is, as you look at it, figure out where you're going to put the D and the P and what they should look like in this pseudocode. Okay, so take a few minutes to do that. I'll get you started because I'll do the first part. I have a hint, if you like. This for loop is written in such a way that V is the current vertex that you're working on, and W is the current iteration of the for loop. Okay, so W is the one that's incremented during the for loop. It's one of the adjacent vertices. Okay, anybody want to tell me where P and D update go and what they look like? Oh, I know. I'm going to write it down. I'm going to write it down wrong, and you can help me fix it, okay? So we're going to put it right in here because we always did it kind of in this totally new case. You got a problem with that? Maybe that's wrong. I don't know. I'm going to make things buggy, okay? So first of all, I'm going to do this. And I will do this. Okay. Can you help me debug that? Okay, this is the right sign language to associate with it. Where? Yeah? Very good. Okay. So the current known vertex is V, right? And so I'm going to set the next vertex, W, to be the old one, or the current one, plus 1. And then this one is fine. The predecessor of the new vertex is the current one. Okay? All right, any question about that? Okay, good. So then the rest of this, look, it's 1, 2, 3, 4, 5 different things that happen here, just like there were 5 different things on this list. Did you see that? I almost went like this to swipe the screen. All right. I want to know what this box is for. And I'm going to want to know the answer in 2 parts. I want to know this, and I want to know this. What are those first two for loops all about? Initialization. Good. Did you say that? Is that what you said? Yeah. These are initialization. Just to set it up. Say, okay, we haven't been anywhere before. What about that last thing? Ooh. Got it? Very good. Yeah. Okay, so think about that. This is the point. This is what we use to pick up multiple components. So when I drew that picture up there, I actually only drew for you part of the graph. The rest of the graph looks like this. Okay? Here, I'll even keep going with it if you want. Okay? Oh, cool. I don't know why that makes me happy every single time. All right, so now let's think about how this for loop operates. It's going to give every vertex a chance to be traversed, okay? So every vertex up there in that graph has a chance to be traversed in some order. We don't know what order, doesn't really matter. If we hit a new vertex, so let's imagine that it's the first one. We haven't done any traversing yet. We hit one that is new. We're going to call breadth first search, the stuff on the right, on that new vertex. Now, when we do so, we are going to explore everything we can in that component, right? And imagine what that does to all of the vertices in that component. It marks them as explored. What happens then in this for loop is that those vertices are ignored by this conditional, right? So the for loop, when it gets to ones that we've already seen, it just doesn't revisit them again. It goes, oh yeah, okay, I've already been there, until it hits one, say G, for example, at which point it will call breadth first search, and this component will be explored. So embarrassing. I'm just kidding. Here, do you want to turn my ringer on just to get back at me? And then I'll be embarrassed? I actually don't even know whose was ringing. I'm just making a joke. I'm sorry. Okay. And so this for loop will continue until it gives every vertex a chance to be an unexplored vertex. And thus, in the end, all of them are explored. All right, any question about that? Okay. So that's all I have to say about this pseudocode. I do have a couple questions. How could we modify this pseudocode to be a cycle detector? So now instead of a traversal, instead of code for a traversal, what I want is code that takes a graph as input and tells me if it has a cycle. Yo, you have a cycle, yeah? Yeah, very good. Remember what we said before. Anytime there's a cross edge, there is a cycle. It's a proof of the existence of a cycle, probably more than one. And so we can, indicate that fact either by setting a flag that no, your graph is not acyclic, or yes, it does have a cycle, or yell out, yo, excuse me, there's a cycle here, precisely when we detect a cross edge. Okay, good. So I'm just going to write that here. Yo, cycle, like this. And you can do with it whatever you want, depending on your context. Okay? All right, fine. How would I adapt this code to, instead of a traversal, be a component counter? What am I going to do? I don't want to traverse this graph. I want to count the number of components in a given graph. How am I going to change it? Yeah? Yeah? Yep. Good. So I'm going to say int count equals 0 here. And every time I call breadth first search, I'm going to do count plus plus. Okay? Any question about that? Is that what you intended? Yeah. Good. All right. Any question about it? So you thought today was all about traversal, but no, in fact, it's about counting components and detecting cycles. All right. Anything else about this? Any questions about it? What do you think my next question for you is? What's the running time? Okay, I don't want to go there yet. What do you think the running time is? If I tell you that the number of vertices is n and the number of edges is m, what do you hope is the running time, or what do you suspect is the running time? Yeah? No. So I didn't hear everything he said, right? Because it's hard to hear the distinction between m's and n's, but I did hear the word log. If somebody comes to you and says, I've got a traversal algorithm that runs in logarithmic time in the size of your graph, you should be extremely suspicious. Why? Because that's sublinear, right? Log is sublinear. Log is faster than linear time. So what does that suggest is a reasonable, do you understand that? Thank you for saying it, actually. It was good. So what do you suggest is a reasonable running time then? Big O of, yeah? M? No, not really. Because I have a graph with arbitrarily many nodes, and it will only always have 5 edges. Oh. So, yeah, what do we need to include? Yeah? Yeah, good. So what we're going to hypothesize is that the running time is proportional to m plus n, right? We're going to have to do something for every edge, and we're going to have to do something for every vertex. And that's what we're going to speculate on. I'm going to get back to that issue of dominant terms and looser bounds in a few minutes, but I want to spend some time figuring out whether this is a reasonable thing as a running time. Okay? Any questions about it before we look at this? All right. So the first thing I want to talk about, the first thing I want to observe is that all of this labeling and bookkeeping, it's all constant time. Updating the P, updating the D, setting the vertices, on queuing, putting things on the queue and taking things off the queue. Those are all constant time. We're going to lump those together and call them processing, okay? Like a process step. And moreover, since they're constant time, we're not really going to distinguish whether or not we're processing a new thing where we had to do 5 of those, or just processing an edge and a vertex that we've seen before, which just means we just have to look at it, right? So all of that is constant time. So what we're going to do instead is look at the iteration structure of the algorithm and assess exactly how many times we have to process something. Okay? All right, so let's go back to the pseudocode for just a minute. You'll notice that the key parts here, the parts that are not constant, are this iteration and this iteration. My first question is, how many times does that while loop execute? How many iterations are included in that while loop? It says while the queue is not empty. Oh my gosh. N times, right? That is every vertex gets put onto and removed from the queue exactly once, not more than once and not 0 times. Every vertex will go on the queue and come off the queue, and that's it. So the while loop executes once for each vertex. Okay? Now, I'm not going to include that as a factor of n, as tempted as I am to do so. I'm going to leave that. I'm going to leave that for just a second. Okay? All right. So I want to talk instead about any individual for loop. What's the running time of any one of those for loops? Yeah? Very good. Remember, those for loops are basically just set up over the incident edges on a given vertex, right? And so each iteration induces degree of V amount of work. Okay? Now, wait a minute. How many of these are there? Wait, there is one for each vertex, right? We are going to set up a for loop for each vertex. All right, what is that? Remember? 2m, right? Effectively, adding up all the degrees over all the vertices is counting the endpoints. You add those all up, it's twice the number of edges. All right, so this is big O of m. Okay, so now, no matter what, this while loop is going to execute n times. So no matter what, we cannot do less work than n, okay? Even if we don't have very many edges. Correspondingly, when we add up all the processing of all the endpoints, we're going to do m amount of work. And so the total is going to be the amount of time it takes to process the edges plus a little bit of a constant more for each vertex to administer the grand while loop. Now, all right, any question about that? So that argues for this, but I want to talk a little bit more about big O and what this means. Anytime you see an asymptotic running time with a sum in it and two different parameters, this sum should be, or sorry, this plus should be interpreted as an OR in the following way. This means M or N, whichever is larger. And in this case, for a general graph, you don't know which one is larger, right? You don't know whether you have more edges or more vertices. M can go everywhere from 0 up to n squared, right? So we're going to leave it like this. We're going to leave it like this because it's more precise than anything else we could give, okay? Any question about that? Any question about it? So if, I'm just going to say it one more time. If your graph, whatever it is, happens to not have very many edges, then this will be the dominant term. If it has a ton of edges, then this one will be the dominant term, okay? But this expression captures all of it. Okay, one more little point I want to bring up. There is a piece of this argument that depends on the fact that we have implemented this graph as an adjacency list. I want to know from you what that is. Where did we assume that the graph is implemented as an adjacency list and not as an adjacency matrix? Where? Where did we make that assumption? You see it? I saw you doing this. Where do we make that assumption? Excellent, excellent. I was just going to give the hint that your explanation should include the letter F in it. So yes, so what he said is the line of pseudocode that says for all W in that adjacency list, right? What if instead of this list, we had had a matrix? How would our argument change? How would our argument change? So instead of this, we're going to have a whole row here. Let's see, how many of them are there? There are 8. 1, 2, 3, 4, 5, 6, 7, 8. And D would have something. D and G would have something. Okay? So H's row in an adjacency matrix would have only 2 entries. So that for loop would have to, in total, navigate all the way down the row, right? So this for loop right here, each iteration, I meant of those iterations, sorry, each of those iterations, the for loop is going to give you a degree of V. Instead of that, you'd have N. That's right, you'd have N. So what does that do in the overall picture? It means that this is big O of N squared for adjacency matrix. Okay? Any question about that? Is what it is. All right. Let's see. So, no questions about breadth first traversal? I'm going to summarize what we did here for breadth first traversal really quickly. And then we're going to talk a little bit about depth first traversal, but not very much. Okay, so the observations, the key parts about traversal in general are a couple of them because they will be true for depth first traversal as well. But a couple of them will apply specifically to breadth first, and I'll break them apart. So the traversal can be used to count components is one thing. And so what's the running time of the best algorithm you know of to count components? It's big O of M plus N, right? It's exactly the same algorithm. Okay, so if anybody ever quizzes you about that, you know it because you know that it's very simple to add to the code to create the algorithm for counting components. All right, fine. Traversal also can be used to detect cycles. Okay. Now those will be true of depth first search as well. So the D structure, which is really just a map, gives shortest distance from start to every other vertex. And similarly, P gives the path. and I mean shortest path. And yes, you might have to print it out backwards and reverse it, whatever. Okay, so that's part of why we did this. Now I want to say just one little thing about that. It means that actually in the context of breadth first traversal, the start vertex can matter, right? You can use this same code to do something more than just traverse a graph by starting at a vertex that's interesting to you. The last thing, which we really don't exploit anywhere in this class, is that the endpoints of the cross edges will have shortest paths to the start that differ by no more than 1. Okay? So suppose UV is a cross edge. Then du minus dv, that is the difference between them, absolute value, is less than or equal to 1. That is, cross edges will not go across many levels in the structure. They basically effectively walk around, give you the ability to walk around the start vertex at a given distance or at very close to a fixed distance. Okay? They will differ by no more than 1. All right, any questions about that? Okay, so the next thing we're going to talk about is depth first search. And there are 2 different strategies we can take for doing depth first search. We could take the previous slide and replace Q with stack. That's right. Everywhere we see a stack operation, everywhere we see a Q operation, we could replace it with a stack operation, and we could go through exactly the same discussion. We would lose shortest paths, and we will lose shortest paths because that will no longer be true. But that's a topic for later. But we're not going to do that. I assume that, of course, you could do that. So we're actually going to do a slightly different take on depth first search. We're going to do it recursively. It doesn't really matter very much. We're just going to use the function call stack instead of an explicit stack. And we will do that starting next time.
I feel like people are done with using this.
I feel like we're all done.
Yeah, I think that's fine.
Yeah.
Like they go of n plus n, would it be correct to like say they go of like max of n for n?
Sure, that would be fine.
Oh,
But you get that same thing with the sum.
okay. But like they still like construct the same.
Yeah,
Okay.
yeah, exactly. And I think you can even prove that. Like, I think there's a,
Oh, okay.
like that would be a proof that you would do in
274.
or 173.
Oh, okay. Sure. Thank you.
Wherever you see the definition.
Okay. Thank you.
Yep.